What is going on, guys? Welcome back. In this video today we're going to go through a full machine learning process and we're going to do demand forecasting in Python. So let us get right into it. Alright, so for this project today we're going to use a Kaggle dataset called demand forecasting. You will find a link to it in the description down below. And when we take a look at it, we can see the columns are quite easy to understand. We have a record ID, which is basically just a row number. We have the week feature, which is just the starting date of the week. We have the store ID, which is the identifier for the individual store. We have the SKU ID, which stands for stock keeping unit, so the item ID. We have the total price, the base price, and we have two binary features indicating whether the item is featured or displayed. And then we have also the target variable, of course, the units sold. So this is what we want to predict. We have all this information here and we want to predict how many units are sold in a specific store in a specific week of a certain item. That's the goal that we're trying to, or that's the thing we want to predict here. Now, what we're going to need for this video is only the train file. So we don't need the test file because this was actually, I think, a competition or something, or is copied from a competition, I don't know. But the test file doesn't contain the unit sold variable, so we don't have the answers. So this would just be to create such a submission file, but to actually build a model and evaluate it, we're only going to use the train file and we're going to split it into training and testing data. So that is going to be our data set, just the train file. So download it, rename it to something like train CSV, and then we can get started with the coding. Now, I'm going to use a Jupyter notebook here. I recommend you do the same. You can, of course, do all of this in a single Python file, but when you do data science and machine learning, it's always better to have these individual cells that you can run, because then you can train a model and use it without having to constantly restart your script. So we're going to use a Jupyter notebook, and we also need to install a couple of packages. So open up your terminal and type pip or pip3 install, and we're going to need the following packages. NumPy just as a basic for everything else, pandas to work with the data frames or with the data frame, matplotlib to do visualizations, and of course scikit-learn to do the machine learning. We're going to do traditional machine learning here, so we're going to train a random forest model. So we're going to need scikit-learn and not necessarily TensorFlow or PyTorch. So install these packages, and once you have them, you can get started by importing pandas as PD. Let me just briefly save this file as main. What we're going to do now with pandas is we're going to load the data frame. So we're going to say df equals PD read CSV, and we're going to read here the train.csv file. And then we can take a look at the data. And when we do that, we will see something interesting. Almost all the features can already be used right away and can be fed into a model. So the only feature that requires some minor pre-processing is the week, because it has 3 numerical values separated by slashes, so it's a string or a date. But the rest of the features can be used right away without pre-processing. Now, whether that's a good idea or not, we're going to see that, but my approach here is to go and start right away with a baseline model, with a naive model, you could say. Just take the data, feed it in, and see what the performance is. So the only thing that we're going to do for this first run is we're going to just take the week feature and split it into day, month, and year. So I'm going to copy this, or actually I'm not going to copy this, I'm going to add a new cell. I'm going to say here df, and then I'm going to get the columns day, month, and year. And that is going to be the result of saying df week, taking this as a string, so str, and then splitting on slash. And the important thing here is the expand equals true. So we want to expand this into multiple columns. And now when we look at this, we have these columns here. And the only thing left to do is, of course, to drop the week column. So then we can say df is equal to df drop. We want to drop the week column, so axis equals 1, because we're dropping a column. And then we have a data frame that we can use right away for training a model. So we don't need any pre-processing to make it at least possible. It might benefit or it might be beneficial, but of course we can do it. So what we're going to do here is we're going to say from sklearn.ensemble import random forest regressor. Now, why regressor and not classifier? Because what we're doing here is trying to predict units sold, which is a numerical value. It's not a class label, so we're not trying to classify the information as belonging to one or to one category out of multiple categories. We're trying to estimate a number. So we're using a regressor here. And what we're also going to do is we're going to say from sklearn.model selection import train test split, so that we can use our data set and split it into training and testing data. For this, we're going to say xtrain, xtest, ytrain, and ytest is going to be equal to train test split. We're going to split x and y. Actually, we need to define x and y first, so let's do that. X and y are, of course, going to be just all the data except for the unit sold is going to be the input, so x, and the unit sold data will be the output, so y. So we're going to say here df drop, and we want to drop the units sold. That is going to be our input, and the output is going to be just that unit sold. And we want to have here a test size of 0.2. So 20% of the data is used for testing. And what we're going to do now is the naive approach, just create a model, random forest regressor, njobs is going to be equal to -1, just so we use all the cores. And then we're going to say model fit xtrain, xtest, not xtest, ytrain. There you go. So this is going to fit a model. This is going to train our model based on the data, and this resulting model can be then evaluated easily by using the score function, model score, xtest, and ytest. This is going to give us an r² metric, so it goes between 0 and 1. Now, I don't like this metric too much, so I want to use something that gives me more of an understanding of what we're actually talking about here. So what I want to have is I want to have the root mean squared error, the RMSE, because it gives me something that I can relate to. It gives me a number that shows me what the root mean squared error is. So I can say from sklearn metrics import root mean squared error, and then I can say that the predictions my model makes is model predict the test data, and then I want to say that the RMSE is going to be equal to the root mean squared error of the y predictions and the actual results. And here I get 29.9. So what this means roughly is this is also in the units. This is also in the correct unit of the units sold. So this is actually units sold. And whether this is good or not depends on what our distribution looks like. So for example, if I go to data frame and I say df units sold, and I say describe, I think that was the function, right? I get the statistical information. So the mean value is 51. The standard deviation is 60, which is very high actually. So since the standard deviation is 60, 29 doesn't seem too bad, but it's also not very good. The max value here is 2,876. So what I can also do is I can plot a simple histogram by calling the hist function. And this already shows me something that is probably very problematic. I have a severe outlier here. I have something, this max value here, 2,876, which is way too large. And all of the data is basically here on the left, and almost none of the data is here, which means that this could be very problematic. So now we get to the part where we consider whether using preprocessing and preparing the data properly can be beneficial. So we will take this score here as a baseline, or actually the R2 score and the RMSE metric here. We're going to take those as a baseline, and we're going to see if we can improve them just by changing how we work with the data. So maybe to also visualize this in a different way, we're going to say import matplotlib.pyplot as plt, and then I'm going to do a basic scatter plot of the data, so plt scatter, and then we want to plot the y prediction against the y test data, and we want to say plt plot, and I want to plot a line through them, so basically the identity line. So I'm going to say np linspace y prediction minimum to y prediction maximum. And here I want to do the same thing with the test. So y test minimum and y test maximum. NumPy is not defined, so we need to import it. NumPy as np. There you go. And probably we should use a different color here. Let's say color equals red. There you go. So you can see this is what our data looks like. We have the predictions on the x-axis and we have the actual values on the y-axis, and they're not very... The ideal prediction would be the red line, so they would always be the same. But you can see that they are quite apart, especially when we get to larger values or to larger values. So this is not very good. Let us keep going now with the exploration. So let us first of all drop the record ID, because the record ID doesn't contain any information. The record ID is just a row number, and it doesn't give me any significant information. So I'm going to drop this feature. We already turned this into multiple features, and now the important thing would be to see what are the distributions of the different features, because we saw that this is not a good distribution, but maybe other features also don't have very good distributions. So let us go ahead and say the following. plt dot, or actually not plt, df hist, so plot a histogram for every column. We're going to say figure size here is going to be equal to let's say 15 and 8. And then we're going to say plt show to get a better visualization here. Now we can take a look at the different features. Yeah, we can already see this is not a very good distribution. And for the other features, we can see that these two seem kind of skewed, but I think that's okay because we have these binary features here and most items are not going to be displayed and most items are not going to be featured. So I wouldn't necessarily change something about this. This could actually be a very significant thing. I would definitely change something about the units sold. Probably we should cut off values after a certain threshold. And another thing that I see here, I mean, not actually in the histogram, but another thing that's important here is store ID and SKU ID. I'm not sure that they should remain numerical features. They are numerical features, but of course the problem is that they are identifiers. So the numbers don't mean a lot. Maybe there is some time information in there, so which store was created first, but for the most part, the location of the store, for example, is much more important than the number. We don't, of course, have the location, but the identifier doesn't really tell you much about the store, especially when it's larger or smaller. It doesn't have an effect. So it's not something that is placed on a scale. It is much more like a categorical value. So what I would do here is the following. I would say we need to handle the distribution here and the outliers in the unit sold variable. We need to drop the record ID, and we should look at these two identifiers to see how many unique values do we have. Maybe it makes sense to do one hot encoding here. So we're going to scroll down here and I'm going to do what I just explained. We're going to start by dropping the record ID. So df equals df drop record. What was the name exactly? Record underscore ID. Axis equals 1. And then, as I said, we want to see, okay, what are the different values here for store ID and SKU ID, or how many unique values do we have? So let's go and say store ID unique, and then length of that. And we can see we have 76 different stores. Let's do the same thing for the SKU ID. And we can see we only have 28 different items, which is interesting. So it makes sense, or it can make sense, to one hot encode these features, which is what I'm going to do here. So I'm going to attempt to take the features from a numerical representation to a one hot encoded representation where every possible value has its own column and can either be 0 or 1. Because I think that a store that has a very similar value doesn't have to be very similar to a store that has a close value. So for example, I might have a store with the ID 8005, and this store might be extremely similar to a store in all its features, which we don't have here, but it could be very similar to a store with the ID 5067, for example. But it could also be the case that the store 8004 is completely different than the store 8005, which is why I think it makes sense to take the stores and represent them as individual features. Is it this store? Yes or no. So one store will be set to 1, all the others to 0. And in this way, it gives the feature, I think, more relevance and more information. So we're going to do this, and then we're also going to take a look at the units sold. Now, the important thing is we already saw the statistics, so I can call the describe function again. This is way too large if you look at the other percentiles here. So what I would want to know is what is the 99th percentile. I think there's the quantile function for this, and we do have here 283. So what I would like to do is I would like to drop all the values that are above this threshold. So I would say df is equal to df, where df units sold is less than this quantile. And now I have, how many columns did I lose? I lost a couple of them, but not too many. So yeah, we lost like 2,000 rows, sorry. We lost like 2,000 rows here, but we now have a much better distribution. So if I call the hist function again, maybe just on the units sold, we can see that this looks much healthier. So I can say bins equal 20 or something to get, yeah, more steps. But maybe you can even go lower. Maybe you want to say something like the 90th percentile. What would that be? Let's see. Let's say df units sold quantile. I mean, now it's going to be a different one, obviously. I'm not going to do that, but you can play around with that if you want to. It definitely looks much better now. So we did this. Now let us turn these two columns into one hot encoded features. So how do we do that? We do that here with the getDummies function in pandas. So I'm going to say here that we want to do a pd getDummies onto the df store ID. The prefix for this is going to be equal to item, to store, just so we know what we're talking about. And then we're going to drop, of course, the store ID column. We're going to take that. This is going to return us this. So we have for each store a column, either true or false. Most of the time, it's going to be false because every single column is going to be set to false except the one that's true. We now want to take this and join it with the original data frame. So we want to say df join with that. And now you can see we have the columns in our data frame, but we also want to drop, this is where we now have to do it, drop the store ID column. And now we can take this and store it into the data frame, and we can do the exact same thing for the SKU ID, just with the prefix item, SKU ID, and that should result in a data frame where we have all the stores and all the items as individual columns. And now we have a bunch of columns, as you can see, 112 columns, which is manageable. If you had 1,000 different items and 1,000 different stores, probably it's not a good idea. But with, 76 and 28, it's totally fine, I guess. And yeah, that's actually what we are going to do here now for the pre-processing. So let's see if this already improves our performance. So I'm going to say here again, model is equal to random forest regressor n jobs equals -1. And then model, actually we need to do, now we should probably do the same split. So we should actually go and say random state is 42, for example. So let's run all of the code again to make sure we have consistent results, because otherwise maybe we increase or decrease performance just because we did a different train test split. So now here we have 0.77, we have 26.99 as an RMSE value. Let's run all of these again. And now we're going to say here that x and y are going to be equal to df drop units sold, axis equals 1, df units sold. So xy is equal to that, and we're going to do the same split. So x train and x test and y train y test is going to be equal to train test split x and y with a test size of 0.2 and a random state of 42. Now this is probably still not going to be the same because we dropped values, but I think that's as much as we can do here. And what we're going to do now is we're going to say model fit x train x test. Yeah, why do I only make these mistakes when I'm recording. X train, Y train, of course. And then model score X test, Y test. You can see that the model now takes more time to train because we have more columns. So of course it's going to take longer because we multiplied the column amount by, I don't know, 20 or something. And now we get 0.82 or 0.827 as the R squared score. So let us see what we get if I say prediction is equal to model predict X test, and then I say RMSE is going to be equal to root mean squared error, where we get the predictions and the test data. And we get 17.7, which is much better compared to what we had before. What was it? 26. So this is much, much better in terms of R squared and also in terms of the root mean squared error. So this is very, very good. This was definitely an improvement just by pre-processing the features in a different way. Now, scaling is not going to help here because the random forest model is not dependent on scale. If you use something else like a k-nearest neighbors classifier or something, or a k-nearest neighbors regressor in this case, then of course everything that involves a distance measure should be scaled. But in the case of a random forest regressor, it doesn't really matter. But what we can do to further improve this is we can do hyperparameter tuning. Now, before we do that, let me actually visualize what we visualized before this here to see if it now looks better. Which definitely it will, but let's see how much better. Yeah, this is now way, way better because we have all these points pretty close to the line. It's definitely much better than what we had here. And definitely also because of the outliers. All right, so that is already an improvement. Now let us do the hyperparameter tuning. Now when it comes to the hyperparameter tuning, I'm not going to do a very complicated one. I want to show you more the idea behind it and what you can do with it. I don't want to run too many trainings here because it's going to take forever. But the basic idea is you say from sklearn.model selection import either grid search or randomized search CB, and you define a so-called parameter grid, at least when it comes to the grid search. And this parameter grid contains all the parameters, all the hyperparameters that you want to play around with. So if I say, for example, param grid is equal to, and then I have this dictionary here, I provide a parameter name. You can look these up in the documentation. One example is n estimators, so how many trees we want to have in our random forest. And let's say I want to play around with different values. I want to try 100, I want to try 150, and I want to try 200. Then I also want to say that I want to play around with different values for the min sample split. And here I could say, for example, 2 or 3. Now, what's going to happen with a grid search is that all of these are going to be combined. So if you have, let's say, a bunch of these different features here, or a bunch of these different parameters, it's going to try all the combinations. So it's going to try this, with this, with this, with this, with this, with this. And then it's going to try this, with this, with this, with this, with this, but this time with this one. It's going to go through all the combinations. So the more parameters you specify here, and the more parameter values you specify, the more runs you're going to have, the more time you're going to invest. Now, if the model trains like this, it doesn't really matter. But if it takes some time, this can really be a problem. So in this case here, if I open up my calculator, now I don't need the calculator for this simple calculation here, but of course we would have 3 times 2, which is 6. So in this case, we have 6 different combinations. Now, if I add another feature with 3 different values, or another parameter with 3 different values, I would have to multiply this by 3. Then maybe I add another one times 3, and so on. Now, this is not the only thing. Since this is a CV, which stands for cross-validation, we're going to train and evaluate the model in multiple combinations. So if you do a 3-fold cross-validation, whatever the number is, you take it times 3 again. If you do a 5-fold cross-validation, you take it times 5. So it could already lead to something like 270 training runs, which can make sense if you want to deploy the model, but for the tutorial it would be too much. I think already this is going to be too much. But what you do here is you say that you define a model, random forest regressor. You can still specify njobs equals to -1. And then we say that the grid search object is equal to grid search. What are we doing? We're looking for the optimal hyperparameters for the model with the parameter grid. Verbose equals 2 is just to see more output. And CV equals 3 means we do a 3-fold cross-validation. And then we can just say grid search fit X and Y. Now I'm going to keep it simple here, and I'm going to just do small values. This is definitely not going to improve the model, but let's go with 10, 20, 2, 3. So we have 4 runs times 3 is 12. And if I do this, you can see it tells me exactly what it does. 4 candidates, so 2 times 2. 3 folds for each, so we have 12, sorry. And this is quite fast because we have very small models here. But of course, you want to do this with larger values. You want to do it with more parameters, so it's going to take some time. So this, what we get here, is not going to improve our model, obviously. But what we can do is we can get the best estimator afterwards. So we can say that the best underscore model is equal to grid search, once it's done training, of course. And this will have something called the best estimator with an underscore. So it's going to be best underscore estimator underscore. We can also look at the best parameters. So I think, or can we? Best parameters, there you go. So in this case, it's 20 estimators and min sample split 3. Of course, if you increase this to 100 will be the best one, but not necessarily always. So it's not always the case that more estimators is better. But in this case, we can just say best model score X test and Y test. And actually, I think, oh yeah, because I trained it on all of the data, of course, it's going to be, of course, it's going to perform well. But if you train it only on the training data, it's not going to perform so well on the test data. But that's the basic idea. You define the parameters that you want to play around with. You want to fine tune, or you want to hyperparameter tune the model. You want to get the best model, the best parameter combination. You want to see how it works on the training data. And then when you get it, you can evaluate it on the testing data. And then you can deploy the model if you want to. So let's run this one more time. It's going to have one more iteration here. And then it should give us the optimal results. And in this case, we get 0.82, which is actually, yeah, just slightly worse than the previous one. So maybe this is not too bad, but I think if you increase the number of estimators and you play around with different hyperparameters, you're going to get even better results. So yeah, this is how you can do demand forecasting in Python. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.